Hello friends, and welcome to a lecture on application of Python to chemical engineering. Today we will be taking up a very interesting problem. The problem is that a system follows Raoult's law, a binary system follows Raoult's law, and we have to plot the TXY plot. Now, all of you at the outset, let me tell you, this is not an easy task. If you try to do it using your calculators, it's really a very difficult task which will not happen. You require computers to do it, but TXY plots are required. TXY plots are required to solve problems in batch and binary distillation problems and continuous distillation problems. So this is one of the most essential things that one must know in chemical engineering in case we wish to design distillation columns. Now, let's take up a comprehensive tutorial today on how to plot a TXY plot. So I have the binary system on the screen. It's that of chlorobutane and chlorobenzene. The saturated vapor pressure of chlorobutane and chlorobenzene is on your screen. And it is given in the form of Antoine's equation. So ln P sat chlorobutane is equal to A minus B upon T plus C, where the values of A, B, and C are written. And similarly, we have an equation for the Antoine's equation for chlorobenzene 2. And the system, as indicated earlier, follows Raoult's law. So for Raoult's law, we have P is equal to x1 P1 sat plus x2 P2 sat. And which we can rearrange to write x1 is equal to P minus P2 sat, P1 sat minus P2 sat, knowing that x2 is nothing but 1 minus x1. The system pressure for this problem is 90 kilopascal. You can choose any other pressure also, and the steps would be the same. So first, let us declare the variable for system pressure. So P is equal to 90. Now, since P would be reflecting in many of the calculations, so it is better to fix its value so that we do not have to each time enter 90. And the advantage also is that we can run the program by choosing a different pressure altogether and get the results. Now, the first thing that we need to do is we need to write the models for getting the vapor pressure. So def VAP PRES CBUT, that is that of C-butane. Now the variable, input variable here is the temperature, and the RHS of the equation is going to be 13.7965 minus 2723.73 divided by T minus 218.265. That's it. And the vapor pressure is equal to NP dot exponential RHS, and we return vapor pressure. Now NP is short for NumPy, so we have to import the NumPy library. So let's do it here. So we import NumPy as NP and we run this, and that's it. So we are done with this model for the vapor pressure of chlorobutane. Similarly, we should be writing a model for chlorobenzene 2. So let's copy this out and paste it here. And we rename this as BEN and we change the constants. So the constant is now going to be 13.8635 86 13.8635, and B is going to be 3174, 3174.78, and C is going to be equal to 211.7. So there we are. Now let's test them. So we write print and we write vapor and we enter the temperature. Let's choose a temperature of 70 degrees Celsius and there we are. So yes, I have missed the word letter S in both cases. So let's do that. And there we are. So what we have here is the value of T, right? And the pressures don't seem to be right. Okay, at 70 degrees Celsius. So let's check the constants have been entered correctly. Yes, the constants have been entered correctly. And yes, a slight mistake that has been done here was I have to put a plus here. Yeah, okay. It does happen sometimes that when you start programming, the plus becomes a minus and the minus becomes a plus. So one should be taking care. And there we are. Now the pressures are right, 77.308 and 13.375 kilopascals. So fine, we have, so far our results are good. They're good and they look good. That would be the vapor pressures. Now we have to find out our TXY plot. Now our TXY plot is going to have two extremes. At X is equal to 0. Okay, at X is equal to 0, the temperature of the mixture is going to be equal to the boiling temperature of the more volatile component. Sorry, the less volatile component, which in this case is benzene. At X is equal to 1, the boiling temperature of a mixture of chlorobutane and chlorobenzene is going to be that of the pure chlorobutane. Okay, I repeat it. In the TXY curve, at X is equal to 0, the temperature, that is the boiling temperature, is going to be that of pure chlorobenzene. And at X is equal to 1, the boiling temperature is going to be that of pure chlorobutane. So the component 1, as shown in the problem or as indicated in the problem, is chlorobutane, and chlorobutane is the more volatile component. So now we need to know the boiling temperatures of chlorobutane and chlorobenzene at 90 degrees Celsius. Now there's a neat little trick to do it. But first learn about this trick. Okay. There's something known as fsolve in Python, and this is a part of the library of SciPy. Okay. So from .optimize import fsolve. So we import the library and now I will show you its application. So let's take any equation. So we take a equation, random equation, and this equation is in X. Now let me take a quadratic equation in X. So the quadratic equation in X is going to be y is equal to x the whole square minus 5x plus 6. Okay, and we put return y. We write return y. Fine. Then afterwards what we do is we want to find out what is the root of this equation, right? So what do? Well, we write RT is equal to fsolve. Okay. And then we write EQU, and we start with some initial guess of the root. Okay. So the initial guess, let it be -3. Okay. And let's check what is RT now. So it gives you the first root, that is 2. Yes, indeed 2 and 3 are the two roots. Now if you want the second root, all you have to do is make a guess of 7. And there we are. The second root now, we get it as 3. So what fsolve does is, it gives you the root of any equation that has been given to it. Okay. Now we can use this to our advantage. How do we use it? Okay, now let's use fsolve to get the boiling temperatures of butane, chlorobutane and chlorobenzene at 90 kilopascals. So for that, what we do is we write two functions. So we and there it is. So the boiling temperature of C-butane. So we write the output Y will be equal to the vapor pressure of C-butane at the temperature minus P, and then we return the value of Y. Now we similarly write a function for the boiling temperature of chlorobenzene. So we just copy and write this once again, change the name, and we change the name of the function here. Now we are pretty much done. Okay, so let's take RT1. That is, RT1 is nothing but the temperature of C-butane at 90 kilopascals. So fsolve is BOIL, boil, TEMP, temperature, C-butane, comma, let's give some arbitrary start value and copy this out. And write another variable RT2 for chlorobenzene. And print out the value of RT1 and RT2. Okay, so we need to run this once again because the kernel was shut off. So let's restart it. And then we are done. We get the value of boiling temperatures of chlorobutane and chlorobenzene as 74 and 127. Right. Now, the TXY curve is going to have the temperature T as 127 for X is equal to 0. That is the concentration of chlorobutane as 0. And for X is equal to 1, that is the concentration of pure chlorobutane, the temperature is going to be 74. And in between these two values of 0 and 1, you are going to have various mixtures of chlorobutane and chlorobenzene. Now, what will be the boiling temperatures? How do we find the boiling temperatures of mixtures in between 0 and 1? Now, again here fsolve comes to your rescue. So we need to find out what is going to be the boiling temperatures of various mixtures of chlorobutane and chlorobenzene. So how do we go about doing it? First, we create an array of the mixture concentration. So we put X is equal to NP dot linspace 0 to 1 and we take 20 such values. Now we again write the function that we want. So this is going to be temp. This is going to be give me the temperature. So this will give me the temperature, boiling temperature of the mixture that we actually want. Now the input for this is going to be X, and out will come the boiling temperature. Now we again define the function that needs to be optimized. So it's going to be optimized temperature. And here we are going to put in T. So this is going to be Y is equal to first it's going to be X, and then afterwards it's going to be brackets, and we are going to put this value. Now remember this expression. Gives you x1. So we are going to optimize this. This Psat is a function of temperature, right? Okay. So we are going to put it as P minus vapor pressure C benzene T, right? And this is going to be vapor pressure C butane T minus vapor pressure C benzene and T, right? And this is going to be minus of X. So when we optimize this function, we will get the temperature for the concentration of X that we have input. And then afterwards what we are going to do is we are going to return Y. Okay. Now we have to return the value. First we have to find the root. So we write fsol T temp and 50. That's it. And then we have to return the value of RT1. So we return the value of RT1, RT. Okay. So now we are done with this function. Now what we have to do is we have to call this function and check it once. So let's call it temp. And let's put a value of 0.2 and let's see what do we get. So let's print it out. print, there we are. So for a mixture of concentration 0.2, we get a temperature of 109. Now best test would be to put a value of 0 and we should get back 127. Yes, we do get back 127, which was the boiling temperature of pure chlorobenzene. So we are done. So now what we have to do is we have to define an array, temperature array. T is equal to np dot array. So temperature now is a blank array. After doing that, we write a for loop. X. So we write a for loop for all the values in X, and then we calculate the temperatures and we feed it to the array. So for this, what we do is we write T is equal to np T dot a ppend append T comma temp temp and X I. So now this will loop through all values of Xi and it will calculate the temperature for those concentrations and append those values to the temperature. So there we are done, and let's check it out. There we have all the values of temperatures for all the concentrations. So all it needs to be said is that for zero concentration, that is for pure chlorobutane, the boiling temperature is going to be 127, and for pure chlorobenzene is going to be 74.1734, and for all mixtures in between these concentrations, these are the temperatures. Right. Now we need to find the value of the vapor phase also, the vapor phase concentration, that is Y. Okay, now how do we do it? We make a separate array for Y. Okay, and that is it. And now Y is calculated using a for loop once again for I in range 0 to length X. Okay, so for all values of X, this is what it means. Range means from 0 to the last one would be the last value in X. Okay, now this is going to be Y is equal to Y np dot append Y is equal to, now how is Y calculated? It is calculated by Xi multiplied by vapor pressure C butane, and the temperature, we input the temperature, the corresponding temperature of the corresponding value, that which corresponds to Xi, and we divide it with the pressure. So that's it. So we are done. Now we get the corresponding values of the vapor phase concentrations. Now the best way to find whether all this is right or wrong is to make a plot. So for that we import the libraries. So we write import matplotlib.py as plt. So we have imported all the libraries. So let's first write the labels. X label is going to be X, Y. The Y label is going to be T. It's not S labels, it's label. And then afterwards, now we put the plot. So the first plot is going to be X, T. And the next plot is going to be Y, T. And after that, we plot the grid and we plot the legend. And there we have the TXY plot. Isn't that great? Now, this entire program has been written in such a way that if you want to calculate the TXY plot at any other temperature, that was the reason why I first defined P as a variable and set it equal to 90. I can do it for, let us say, 85 degrees Celsius now and run the entire program. That's it. Now you have it for 85 kilopascals. Now for 85 kilopascals, let us have a look on what would be the boiling temperatures. The boiling temperatures, obviously, when the pressure has been reduced, the boiling temperatures have also reduced. Now for chlorobutane, it is 72.93 as compared to 74 when it was 90 kilopascal. And for chlorobenzene, it is 125.29 as compared to when it was 127 odd for 90 kilopascals. Now, this entire program can be run for any pressures that you want. And this entire program can also be modified to handle non-ideal VLE, where the liquid phase is defined by the activity coefficients. So it can be modified. Of course, I leave that as an exercise to you. And if anybody has any queries on that, you can always write to me on the comment. So that was all about it. Let's hope you have gained something from this entire video and it helps you in really solving your distillation problems. And please do like and subscribe my channel. That is very important to me. And write comments in case you do not understand anything or if you want a video on certain topic. Okay. So that was it from me. Goodbye, guys. Have a great day and have a great time.